systems for space, or rather jet propulsion systems. I need to be very clear that the propulsion systems that I'm developing through this company, that you hear a little bit more in this presentation, is something like this. This is an actual physical thruster. I know some of you all were present at the Art Science Museum, Moon Gazers, when we actually showed our physical thruster down there. Now, at that point of time, we haven't test fired. Happy to show later on that we have actually physically verified the concepts down there. There's a lot of deep and rich physics that people don't seem to get at this moment. So this is based on a Hall thruster, but it's a Hall thruster that you've never seen before. Okay, I'll explain more on the parameters or rather principles of operation of my systems later on. Therefore, I'm trying to say that my propulsion system is not a propulsion system that enables platforms to lift off the ground. Okay, I will not be talking about that today. I'll be talking about the kind of low thrust propulsion systems that enable satellites up in orbit to do very fanciful maneuvers. Okay? Sorry, I got candy in my mouth. Okay, the structure of my talk. This deck of slides, right, I've been using for over 15 plus presentations for the last week or so. I was in the Northern Territory. I was giving presentations to primary school kids, high school kids, the guys from Darwin University. I was also giving presentations to the non-territorial government, so government officials and people who are experts in the field. So it's very wide, diverse, broad. I aim to cover two main things only. Number one, I feel that those who do not know opportunities there are in space, especially in Singapore for the space industry, I hope to be able to highlight that there really are opportunities for everyone to do certain things and for us to strategically do something good in order for it to be economically sound for us to build up this industry within Singapore. The second thing that I will be covering essentially will be a little bit, if you will allow me to indulge myself, in the technology behind the plasma rockets that I'm developing. So I'll talk a little bit about plasma physics. Just indulge me probably about 1 to 2 minutes so that you physically understand and appreciate the science behind the systems that I'm developing. And possibly one day, you can develop systems like this on your own, and then I can retire and can do something else. Okay? Superb. Now let's see whether I can operate this. Oh, I didn't on. I like controller, huh? Okay, then I can do this. I can do it this way. Okay, as I have overrun all my presentations for the past 2 weeks, right? I don't want to go. I already know what kind of rubbish I'm going to talk about, which kind of things are not important to talk about. My current involvement, right? I serve as adjunct assistant professor with NTU. I'm principal investigator there. I currently helm a startup called Aliena, and you've heard about this earlier on. We do propulsion systems. What else am I doing? Oh yeah, I'm also serving as expert in residence appointed by the Australian Northern Territory government to Darwin. And essentially, it serves to build up a space ecosystem that bridges relations between Singapore and Australia. My background, I was a pioneering member of a few labs in Singapore. Most notably, the Center of Innovation for Energy, Ecolabs, currently now based at NTU. Pioneering member of a Space Propulsion Center, so that was the real birthplace of propulsion systems in Singapore. I spent a nice part of my PhD down there. I was an adjunct lecturer, I still am. If they call me back, I have to teach with NIE. I recently, I usually wear this tag quite often. I'm still a public service officer. I hold a card with the public service, but I recently just cut. I sent in my resignation just yesterday only. And during my time in the public service, I served at Dunman High School. I see 2 of my students over there. And I spent the rest of my time with the university advising MOE HQ on certain curriculum planning policies accordingly. Okay, so enough about myself. I'll just tell you that I've done quite a bit. It's not just restricted to space propulsion my entire life. And one of the things that I want to emphasize a lot over here in this slide is that over the course of the years pursuing research in Singapore is something that some of y'all might be intrinsically motivated to pursue. Research in Singapore is really championed and motivated by whether a research topic has an avenue or potential to translate into a commercially viable product. Okay, so this is something that you hear a lot. There will be a higher chance for you to be funded if you're doing research if number one is really big science, extremely sexy big science that will win you a Nobel Prize. Okay, if it's in between there, right, cannot win Nobel Prize but still sexy enough to publish in like maybe low-tier journals, right? You really have to look for a commercial slant to it. So looking at the kind of topics that I was dealing with, right, I'm no Nobel Prize winner. Okay, I always had to look for a slant for my research to be have a little bit more impact, and the impact comes in money. So in the early years, right, Singapore really championed for renewable energy, and that's where I spent a great part of my undergraduate and master's in using plasma sources to make solar cells. Again, my first love, right, was really in physics. I live in the era where we haven't discovered the Higgs boson. I really wanted to be a particle physicist, and it's something that I think some of people over here would know. But unfortunately, in Singapore, it's extremely difficult to pursue something like that. So the next closest thing that I could do was plasma physics, high energy physics, and we decided to see what kind of applications we can do out of it. So naturally, photovoltaic cells, very sexy at the start. Nanomaterials, also very sexy. I live in the era where two-dimensional materials, wow, can publish very high impact and sexy papers. So I did a lot of nanomaterials, hoping you can publish a lot of papers. I did a lot of high-density plasma work. And somewhere in the middle of my career, we realized that, there was a lot of haze. And environmental control was very important, a hot topic in Singapore. So we decided to deploy plasma sources to like treat air, treat water. That time got haze. And then at that point of time, Malaysia wanted to cut water supply to Singapore. Then we decided, hey, we can use plasmas to treat water also, ensure water security in Singapore. So the key message, right, that I'm trying to bring across, right, is that in Singapore, though we can be very competent in certain verticals, very, very deeply entrenched, and have deep expertise in particular things, we always need to remember that we need to continuously innovate in order for us to move accordingly. We cannot always remain stuck in our rut. Okay, so one final thing to note, and how I actually evolved to do plasma rockets, or rather propulsion systems in space. Space later on started to become a little bit more attractive because of the ability for us to scale platforms, we call satellites, into very small compact systems that you can deploy multiple payloads on board. And small commercial entities that are emerging players in the market can thrive. And all of these systems, right, as you will see later on, require payloads that we can develop. And we realized that plasmas really could fit in very well. So we applied for grants, we got it, and then it started off from fundamental research, we commercialized, and we spin off. So this is a story that I think a lot from NUS or within the academic ecosystem can take away as well. It's very important to consider or remember that every piece of research that you do within the university has potential to commercialize. You always have to begin your research thinking like that. Before I begin, I also need to acknowledge a few of our partners. I was based in NTU for 10 years. I spent good 10 years in NTU. It's my 10th year anniversary this year. They haven't given me a plug yet. Okay, I need to acknowledge that we are really supported very strongly by Intuitive. I think the similar equivalent in NUS is NUS Enterprise. And I come from physics, or rather science background. I'm a physicist by training, engineer, if you like, of sorts by training. I have no reason to say that I can start up a business and do well. And that needs to be many things that you need to address in terms of legal documents, drafting legal contracts, handling finances. These are things, right, that people who are in engineering and physics, right, aren't very competent with. I'm doing a stereotype, but you have to admit this is not our core competency. The ecosystem that the universities in Singapore provide allows for engineers and physicists like me to actually understand and learn on the job while being able to consult with experts in the field. For example, legal experts, for example, people who have drafted contracts and allow us to speak and understand terms being put out by our investors and so forth. So this is a very nice ecosystem that we have in Singapore, and it's something that you rarely see in other countries. We do see it, but in Singapore it's extremely strong, and I have to acknowledge the kind support from Intuitive for that. In this round of investment, we've successfully raised at this moment an oversubscribed round. At this moment, I don't think I can disclose the amount, but we are supported by CapVista. CapVista essentially is a VC under DSTA, so it's a MINDEF-backed VC. We're also in this round, we also have with us the guys from the Australian Northern Territory government acting through Darwin Innovation Hub, hence showing that we have a G2G backing over here. And we also wanted to have a little commercial slant to it. We don't just want to show that only governmental entities are interested in our products. We also want to show that it has like some commercial value in the things that we're developing. So we got 500 startups, a US-backed VC, to come on board to play with us, right? So this round was oversubscribed by these 3 entities. The next round will be even more sexy. So we hope that we can hold out until the next round. We already have people wanting to whack inside already. So when the next round comes, it'll be interesting. We work extremely closely with NewSpace and SSTA. NewSpace is essentially a spin-off based at SAR as well. And we work extremely closely with them, you will see later on, to design and develop a platform that will be tested in space next year. Okay, next. Okay, 30 seconds. Our team, extremely international, okay, very diverse. We have 4 founders, okay, one Italian, one Romanian. Very strong advisory board. Professor Liu Baochen, scientist, serves as chairman of the board of advisors. Professor Park Sung-dong, founder of Star Trek Initiative, is also one of our mentors, together with Wee Seng from Satellite Research Center. So we are very glad that we can move quite quickly. A very lean team, but very, I don't like to call my team, you can see. Okay. These are the existing facilities resources available for all of us. And that's, again, I would like to highlight one of the very good things about being in the startup ecosystem in Singapore. You get to incubate early phase ideas, and you're given opportunities to fail very, very early on. You're giving access to infrastructure that otherwise you would not have any chance to acquire within the university ecosystem. Once you realize that you have gone out of the gestation period for your technology to mature, and you can start to spin off. So in the early days, even at this moment now, we utilize the clean room for assembly at Satellite Research Center quite a bit. Satellite Research Center, in the early days, they were using very coarse vacuum environments for us to test propulsion systems. We managed to retrofit it with whatever money that we have from our salary to do something for larger propulsion systems. What's happening very, very soon is we are starting to expand already after this first round of investment. We are acquiring an entire test facility at Changi Business Park, and we invite anyone within the ecosystem who wants to develop space-based payloads to come and incubate with us, because we believe that this entire ecosystem can only thrive if everyone plays together. What am I trying to say? Okay, so I'm trying to say that in space, right, there's no chance in hell that my propulsion system is going to sell if someone else isn't able to fully qualify a bus that can go up to space. There's no chance in hell this propulsion system can sell if there's no peripheral payload that will enable advanced communications, advanced data sensing, and Earth observation up in space. We want to be able to show that in Singapore, we can do things very strategically. We are able to miniaturize it. And when the time comes, we have a collection of partners that we can piece together like Lego to build up satellites that will be of interest to commercial entities, and we can send it up to space very, very rapidly. So this is what we want to do in this little ecosystem in Changi Business Park. If you're interested, we can have a little chat about this later on. But we are really trying to put space in an aerospace park. At this moment, it's just an aviation center where they have a lot of 737, A380 trainers down there for budget airlines. But we really want to start putting in space environment facilities down there so that any one of you who wants to develop a space-based payload and want to have access to a space environment simulator, come over there. We'll have the equipment for you to test and qualify very rapidly. I know we talk a lot about this. This is for a foreign site, but in Singapore, the key thing that I'm trying to drive over here, right, is that Singapore, we innovate. This is our way of life, and we don't innovate in Singapore, right? We really will die. That being said, we need to be very extremely strategic in how we invest in the research and innovation that we do. As mentioned previously, our government works on very fixed budgets, right, for research. In fact, we spend quite a bit, but it cannot be the case that we spend $1 billion on something that does not take off or have very tangible effects or ramifications for the economy. In Singapore, in space, this is exactly the same. There's no way we want to invest very broadly into things that will not have immediate tangible benefits to Singapore. You will see later on that Singapore strategically invests in developing certain types of payloads, certain types of platforms, and these are miniature platforms. You'll see this very, very soon. But before I go over there, I need to talk about why we are developing small platforms. Okay, and why we are developing small platforms really comes from strategic trust and initiatives out of Singapore. One of the more popular ones, first announced by PM Lee in 2014, is the Smart Nation Initiative. And really, it's because at that point of time, I think they had some foresight already to see that data will actually drive the economy of the day. And if you don't believe me, right, Wee Sing likes to say this a lot, right? In the public service, when I was a public service officer, or maybe you hear this a lot. The ABCDs of Smart Nation, right, is enabled by data. And the ABCDEs, which are the verticals that form the pillars of Smart Nation, really is in artificial intelligence, blockchain, cloud computing, data analytics, and edge computing, right? If you are in some position of authority at this moment in the public service or wherever, managerial role, and you realize that your company is not doing well, you need to pick on something to improve productivity. There is a chance you hear this a lot in the workplace, someone going up to you and saying, oh, the business is not doing well. Have you tried putting in AI? Or another commonly heard thing is, hey guys, let us deploy data analytics in this so that we can better find out what our customer wants. And most of the time, the people saying this, right, for example, AI is a very good example. Not a lot of people who throw around this word AI, right, know what AI really is. A lot of people who talk about AI really are talking about autonomous systems and not artificial intelligence systems. Okay, so this is one of the things that we bring up a lot. Not a lot of people understand these jargons a lot, but things are changing. The thing that I'm trying to highlight, right, is that data actually is a key enabler to run all of these verticals for a smart nation. The thing that we really require in order for us to enable these 5 verticals really is in 2 things. We need large amounts of data. Another sexy word, big data. Okay, large amount of data. Yeah, big data. You say big data, everybody, what? Or you write grants, right? You put the word big data. Wow, okay, approve. Second important thing, okay, apart from big data, okay, you need high resolution data. It doesn't make sense if I give you 1 terabytes of data, which is low resolution, you can't do anything about it. So these are 2 important things that will really drive the smart nation. Where does space fit in? Now, you can see something like this. If we have platforms, extremely small platforms that fly very, very close to Earth, flying closer to Earth, number 1, gives you higher resolution data. Second of all, it allows for your platforms to have higher revisit rates. Now, this kills 2 birds with 1 stone. Large amounts of data from the fast revisit rates. Number 2, you fly closer to Earth, higher resolution data. The last thing, which is a bit of a soft touch, whenever we talk about ABCDEs and a smart nation, public fuel, I'm not sure if you are aware of, one of the first few countries to deploy these smart nation initiatives was in China. And people always talk about, wow, Big Brother is observing, Big Brother is looking at me. And that's the reason behind it all, right, is because people can physically see cameras all over the place. And people don't like it because they feel that their privacy is being intruded on. So satellite systems, right, they are remote and non-invasive. People don't see, people don't know, out of mind, out of sight, but at the end of the day, you still be able to run your applications accordingly. So we see that satellites and small satellites really are key enablers, right? Okay, so this is what I've talked about. Previously, when talked about space, you think about large platforms, but we see a recent trend where we're not talking about large platforms anymore. We see that things are moving from bigger platforms to things which are extremely small. And platforms which conventionally fly at 36,000 kilometers away from Earth geostationary orbits, they're going closer and closer to Earth. As mentioned previously, flying closer to Earth using smaller platforms, they allow you to get high resolution data, high quality data, and data on demand. Now, the key thing that we want to emphasize at this moment, right, is in the advent of cube satellites. Some of you might have gone through military service in Singapore, and you know that what we like to develop in Singapore, right, is very modular. So you like to pick and choose what you like. So for example, something becomes obsolete, right? You can take out something that you don't like anymore, and then you fit on something which has new capabilities. A good example will be the load-bearing vest. So you are fully able to customize your equipment to your needs, to your applications. So CubeSats are exactly like this. You know, given the gestation period, I've mentioned this before, for various payloads up in space, could be communications, 6G communications. I'm actually working with a company right now to develop 6G communication payload. Gestation period for something like that could be anywhere in the order of 3 to 5 years. And we can't wait 3 to 5 years before we develop something to bring up. So in the intermediate time, right, before we can develop a full platform for these applications to run right, CubeSats also allow for other intermediate platforms to flourish and to thrive accordingly. So we've talked about CubeSats being key enablers because of the sole fact that it's modular. The second important thing about Cube satellites, right, is that conventionally when you deploy satellites, you know those large satellites, right, probably you can deploy for small satellites, probably about 7 to 8 per launch, right? But when you're talking about Cube satellites, you can deploy numerous in orders of tens to hundreds of satellites in one particular launch. Now, remember I was telling you about how satellites at low Earth orbit in equatorial plane, their revisit rates are 90 minutes for one cycle. That means it takes 90 minutes for a satellite to go from one point and then revisit back again. Now, if you think about it, that's for one satellite. And if you fly lower, your orbital revisit rates become lower. That means instead of 90 minutes, maybe you can bring it down to maybe 70, 80 minutes. That's one satellite. Now, the new advent of space at this moment, or rather, what's being championed is not in just one satellite, it's flying a constellation, meaning multiple satellites flying together in a particular formation for it to achieve a particular operation, or rather for it to conduct a particular operation. And this is what we call constellation. Constellations are the emerging trends, and it will severely disrupt the market. This is an interesting slide. Huh? If you see at this moment, 24,500 known constellation-based satellites are projected to be launched in the next 6 to 9 years. Most notably, SpaceX, they want to deploy a constellation of 12,000 satellites for Starlink. Amazon Project Kuiper wants to develop about 3,000 satellites for their own constellation, including all the other countries from US, China, Europe, and others, right? 24,500 known constellation-based satellites are going up at this moment. And this is important for me to highlight, known constellations at this moment. Now, we believe that these numbers will be extremely high later on, higher later on. And the reason why I'm saying this is because, again, there are many terrestrial-based applications that can be enabled by space. But at this moment, they don't find it to be feasible enough because the technology is not mature enough. Given that a lot of us are working in different engineering fields in Singapore or internationally, we do believe that we can further catalyze growth in allowing for payloads to be developed that can complement other terrestrial-based applications accordingly. So 24,500 now, we foresee that this number will grow exponentially. Okay, Singapore-driven endeavors in space really, in the next 2 slides, right, I'll just show you what we have done in space. Coming from NTU, I need to do a little bit of publicity. Singapore, through NTU, sent up 9 satellites, and NTU alone. And all of these 9 satellites, they are all small satellites and below, meaning to say 500 kg and below. You take a look at them, most of them are Cube satellites, okay? Now we look at the rest of the satellites that Singapore has sent up. They really are small satellites and below. And most of them are really Cube satellites as well, okay? So why am I trying to highlight this? Back to my point about strategy in Singapore in deciding what we want to fund and in deciding what kind of things are aligned with national interests. We really realize that having a strategic engagement in the industry allows, or rather requires for Singapore to look at developing very, very novel payloads that can be miniaturized, very small, and they are highly functional. You notice also that a lot of the payloads that are deployed on board our satellite platforms, the people who develop them, they have not a lot of space-based background. For example, the guys who developed the atomic clock, they're from CQT. They didn't have a lot of experience in space. For me, I had no experience in space prior to starting up this company. I was a plasma physicist by training, and I'm working on plasma rockets. A lot of the systems, for example, communication payload, imaging payloads, these guys who are developing these systems, they do not have space background as well. What we in Singapore try to do is we try and harness and utilize expertise from within our faculty, from within our institutes of higher learning, identify and throw out challenge statements to competent people who can develop systems like this to be rapidly integrated. And this, again, is the reason why I feel ecosystem for us to thrive and operate out is extremely important, because when something becomes ready, the guys who are engineering satellites, who have real space experience, can integrate them on board extremely quickly. So I've talked about space in general, the ecosystem in Singapore, and how where the opportunities are for Singaporeans or the Singapore ecosystem in space. I haven't talked about my propulsion system yet, right? This Hall effect thruster. And in fact, a lot of you will ask me, we have already so many satellites up there. Most of them are cube satellites, and not all of them carry a propulsion payload. Do we really need propulsion? Okay, so this is a question that's thrown to me a lot, and I have to answer. So I'm trained in answering this question already. Okay, I got 7 points over here. I'm not going to use 7 points. I'm going to use 3 main points only. Okay, and the first point really is in, remember I talked about coming closer and closer to Earth, flying closer and closer to Earth, and flying in formation. Now, if you think about it, right, it's okay for you to fly at 550 kilometers and have your platform last up there for a good maybe 5 and above years. Now, as you come closer and closer to Earth, the effects of atmospheric drag becomes very prominent. At 350 kilometers away from Earth, your satellites spiral back down into the atmosphere and burns up in a matter of 27 days. Without a propulsion system, imagine you can deploy a constellation up there, right? So for example, maybe I'm a telecommunications provider in Singapore, and I want to whack up 100 satellites at 350 kilometers to do Earth observation in a particular belt. I can do that at a very low cost. But imagine, without a propulsion system, right, the entire constellations, right, I can run the application for 27 days, then to restart. Doesn't make a lot of sense. Okay? A propulsion system essentially allows for the extension of physical lifetime. This is my first point. Extension of physical lifetime of satellites through this maneuver we call drag compensation. So after a few orbits, right, we can fire our thrusters to compensate for atmospheric drag, allowing for satellites to fly for an extended period of time. Now, some orders of some ways for you to visualize something like this would be, you see that coffee cup over there that some of you all have, or bottles of water. On just 100 grams of fuel, barely like half of the amount of coffee that goes in there, you can extend the physical lifetime of your platforms by a factor of 9. So imagine what we could do if we pressurize the system and have about 1.2 to 1.3 kilograms of fuel on board a platform like that. So this is point number 1, physical extension of systems, lifetime of systems. The second important thing that we are trying to enable with propulsion systems is, for small platforms, one of the things that we want to enable is, number 2, agile space. Agile space meaning to say, we want to make sure that our platforms, when they go up to space, they have the ability to control where they are pointing and control their orbital altitude and attitude accordingly. In the past, this was not really possible. It is possible if you expend a lot of fuel. But what the systems we are developing enable is to allow for extended operations in order for you to consume very little fuel, but to perform advanced mission maneuvers. And this will actually have effects on, let's just say, I'm a company running satellites that will empower search and rescue operations, or if I'm trying to help out for disaster relief, doing imaging for defense, and so forth, I need a propulsion system that works on demand for very agile platforms in space. Now, the last thing that I want to talk about, or rather propulsion systems that enable, really is in the creation of sustainable space. And sustainable space is something that is very dear to my heart. It's not something that a lot of commercial entities like to talk about, but I feel that as you guys are over here, there needs to be some values in education also. Recall this. And sustainable space, right, is really talking about ensuring that we know that in about 6 to 9 years' time, we are going to fully deploy assets in space, conducting numerous operations. But we want to ensure that in 50 years' time, the next generation and the generations to follow, they still will have access to space and access to a platform up there to deploy their applications. Why we think that without propulsion systems this is impossible is because of the reason of space debris. Okay, as many platforms go up and they don't deorbit, it contributes to a lot of space junk. Space junk is not being regulated at this moment. Of course, there are regulations put in place by United Nations Office of Outer Space Affairs saying that you should deorbit your systems at the end of lifespan. But at this moment, no one regulates it, right? And the reason really is because there isn't an effective propulsion system, cost-effective propulsion system that will enable debris up in space to effectively deorbit at the end of lifespan. Now, what we want to show, or rather what we want to make available and accessible to platforms, all platforms, any platforms going up, is a responsible utilization of space through provision of a cost-effective, low-power propulsion system for it to decommission, enabling sustainable space for years and generations to follow. Okay, so yeah. I mentioned this before. There are two main types of propulsion, so I'm going to get slightly technical from here on. Not extremely technical though. Chemical propulsion and electric propulsion system. Chemical propulsion systems are the systems that really enable the liftoff and all the way up to a deployment up in space. Now, electric propulsion systems are the systems that we fire up in space that will allow for satellites to fly in constellation and to do maneuvers up in space. The key difference really is in the ability for us to fire continuously for months versus if you're talking about chemical propulsion systems, everything's over in a matter of minutes, okay? And that you expended all your fuel. Why we are able to do this? It's really because it's in the exhaust velocity that I will talk about later on. Indulge me in 2 minutes later on. The exhaust velocities of chemical propulsion systems is about 4.5 kilometers per second. Now for electric propulsion systems, the exhaust velocities is in the excess of 50 kilometers per second. That's like going from one end of Singapore to the other in just 1 second. That's how fast our exhaust velocity of our particles or our ionized particles are as they exceed our thrusters. And that's the reason why we are able to utilize our propellant very, very effectively for it to fire continuously for months. So, yeah, this is a primary school slide. Okay, you all know that there are phases of matter, right? Okay, so I don't need to spend so much time on this. Okay, I go to schools, I ask them, hey, you all know got how many phases of matter? 3 phases. Okay, what's the 3 phases? Solid, liquid, gas. Okay, from one phase to another, how do you do phase change? You add in energy, right? You heat it, you add in energy. So from gas phase, right? So at this point, I'll ask all of them. Okay, indulge me. How many phases of matter are there? 3. No, there are 4. So some guys who are smarter ones will say 4. That's plasma phase. Then you see, I always need to have backup card, right? 4th, there I say already. I'll tell them got 5th phase. Both Einstein condensate below. Okay, so backup card. Anyway, I deal with plasmas, and plasmas really is an ionized gas. You really get a collection of plasma when you add in extra energy to a gas phase, gaseous phase, where you remove an electron or you strip the electrons from the atoms itself, and you get this collection of charged particles, including your ions, your electrons, your neutrals, your excited species. Now, in this soup, right, that we have over here, is really an order in disorder. It's such a beautiful state. Because in plasmas, the sheer fact that you have charged particles, and you understand that charged particles can respond to electric and magnetic fields, means to say that all of us, if we understand dynamics of plasmas very well, we can control, we can sculpt, and we can manipulate how the plasmas work for our benefit. Okay, and that's the reason why I say there is true order in disorder. There's no real order in gas. In fact, you see, from solid to liquid to gas, right, there's really no order at all, right? But when you go from a gaseous phase to a plasma phase, there's so much beauty in the plasma phase itself. And that's the reason why I chose to study plasma physics. Okay, so really plasmas are really present in everyday lives. We see this a lot, and I'm not going to talk about the sun. This is really for primary school kids. We'll talk about fusion. This is for another crowd where I speak to government officials. And we use this for electric propulsion systems. Primary school slide. I try to emphasize this a lot now. It's also very important to all of us. These are the things that are exciting to kids. And exciting, in fact, not just to kids, to all of us. Right? Whenever we talk about plasmas, right, we talk about lightsabers, repulsors, ion cannons, plasma cannons, and so forth. We always talk about weaponizing systems. Right? These are the things that we talk about, but we don't talk about utilizing technology for the betterment of society. Right? This is something that I talk about at the Art Science Museum, and I need to highlight it at every talk. Every time we develop something within the university, within any capacity at all, we should always approach it into thinking that we can always develop systems for the betterment of society. And in plasmas, right, we actually have an International Thermonuclear Experimental Reactor. This is the world's largest scientific experiment. When this is done, we will fully demonstrate that we will be able to have energy self-sustainability in the future. Now, indulge me 30 seconds. For ITER, right, the fuel for a nuclear fusion reaction is just seawater. 1 kilometer by 1 kilometer by 1 kilometer cube of water, seawater itself. The energy that we can extract from it, from a nuclear fusion reactions or nuclear fusion reactions, is equivalent to the current in terms of oil, in terms of fossil fuels, and everything put together in just 1 km by 1 km by 1 km of seawater. And this really is the future for humanity. And that's the reason, this is really my big dream. I work on a lot of fusion systems in the early days. You'll see this is really the inspiration for this later on. I'll tell you why. Okay? It's so easy it's so difficult for us to confine the plasmas in order for us to extract energy out of it. Short-term goal for us, right? For me, I just thought, you just cut one hole over there and then expand the exhaust, and then you get, you get thrust out of it. So it really is something that we thought about at the start. And of course, we're developing propulsion systems over here as well. No, not going to talk about this. Not going to talk about this as well. One last thing that I just want to know, just indulge me 30 seconds. Early aspect of my research before transiting into space, I dabbled in this a little bit. There's some space teams over here, by the way, if you're into space medicine. So this is a plasma torch that I wanted to develop for medicine. And at this moment, I say this a lot in all the talks that I go to. One of the things that I'm very afraid of is at this moment is surgery. And surgery, I'm afraid of surgery here because when you go through a surgery, a surgeon is involved. A surgeon is human. So I always imagine, I still have this phobia of surgery. If I have to go through an eye op, right, then a surgeon is operating on me, then he sneezes. Oh, finished, gone, blind, rest of your life, right? Or the surgeon the night before had quite a bit of drinks, never sleep, but next day still need to put money on the table to pay for the drinks that he spent the previous night. So go to work, tired, sleep, die. Okay? The world will be a much better place, right, with robotic surgery. Okay, and this is something I always believed in. Access to robotic surgery, right, will not only enable higher rates of survivability in terms of operations, but it will also enable, access for medical treatment to places that can't afford it. So all you need is just a mobile platform for something like this. If you make it open source, right, anyone can have access to these kind of treatments accordingly. My contribution at the start that I thought I wanted to be a part of this would be a plasma system. It's an all-in-one plasma torch. I thought we could do it. It's still open topic. Anyone who's interested can work on it with me. Really, it's in a plasma torch, all-in-one. So at the first phase of the experiment, you have the robotic arm, right? So all the robotic arm needs to do, right, is to just grab hold of one tool, which is my plasma torch. That plasma torch uses plasma to disinfect the surface. After that, it increases the temperature of the plasma to ablate the tissue, so that you can make the incision and have access to tissue inside. After that, you can increase the temperature further and achieve certain density of reactive oxygenated species to treat ailments, for example, to remove tumors or to apply heat at particular regions, afflicted regions. And last but not least, you can lower the temperature a little bit and tune the density of certain species so that you can promote wound healing. So this is really an all-in-one system that I feel has potential to impact the biomedical sector. If we're talking about space, this is also important how I pitch it to the guys from the space community. I always talk about in space, let's just say astronauts suddenly got something wrong, they need operation. You can't fly a surgeon up there to perform the operation, right? So imagine if you have a robotic medical treatment facility up in space. All you have to do, right, is when the spacecraft makes a pass through ground, you beam up the algorithm for you to perform the surgery. The robotic platform does the surgery for you. So this really is the future. But again, I'm here to talk about space. So again, I have just one slide, right, which is a bit technical. And some of you who have gone through my classes in school, right, I love math, but I can't bring myself to solve the equations on my own. I give it to a mathematician to do it for me. So whenever I talk about physics, right, I always feel the physics. I always like to tell my students to feel the physics. And this actually encapsulates all of rocketry, right, in just one Gedanken experiment. A Gedanken experiment is a thought experiment that all of us can feel. Okay, and we can imagine ourselves in this spot to really visualize how we can exploit certain parameters in order for us to optimize our systems that can operate in space. So let's just say, at this moment, you got those roller chairs down there, right? Okay. So imagine you're on a roller chair over here, and you want to go from this place to a target of interest. I think I've talked about this before. I give you two things. You can either use fish balls, or you can use a watermelon. Okay. Do you throw out fish balls, okay, which are relatively low mass, or do you throw out a huge watermelon in order for you to achieve the highest effect for you to go from this place to the other? Naturally, you will say, I'll use a watermelon. You can feel it lah. You've probably done this before. You know, you really, yeah. Let's just say your friend down there, then you just down here, you throw a heavy object for you to effect larger change. Okay, so naturally you identify that heavy mass is important. Second thing, okay, you identify that you want to use a watermelon already. Do you throw it slow or do you throw it fast? Okay, you have two options. You can either just take the watermelon, throw it out like that, just let it drizzle out, or do you charge it up and then you push it out at extremely high velocities? Naturally, you will say that you do it very quickly as well. You charge it up and you push it up at extremely high speeds. We realize that forces are really mass and velocity dependent, and this actually encapsulates forces equals to the time derivative of momentum over here. This really is in the secret sauce of my propulsion system over here. Point one, how do I make my propulsion system or my Hall effect propulsion system very, very effective? If we look at the mass that we deploy, okay, in the propellant that we deploy, we need to use heavy mass, right? Something which is extremely heavy. The propellants that my propulsion system deploy, they are xenon. They can be krypton. So any group 8 is group 8 to the bottom. I don't know whether you call it group 8 now. Maybe now it got changed in IU back already. Group 8, last time, okay, when I A-levels that time. Group 8, bottom right, xenon. Heavy, but at the same point of time, is inert. There's another good thing about xenon, okay, bottom right, that it's so large, right, that the ionization energy, if you remember your A-level chemistry, the first ionization energy is very low because it's the valence electrons so far away from the nucleus itself. So all it takes in order for you to have that first ionization event, for you to generate that plasma, is not a lot. That's the reason why I can miniaturize it and operate at such low powers. Second important thing is, you know that, okay, we deploy heavy propellant. Second thing that we need to do in designing a propulsion system, right, is to think about the velocity, exhaust velocities. Now, there are cold gas propulsion systems being developed at STAR at this moment. They are cold gas. They deploy extremely heavy propellant, and all they do, right, is they open a nozzle, the cold gas exits, and then you generate the thrust, right? What we are trying to do, or what my company is trying to do, is to, instead of just open a nozzle and let the exhaust flow out, right, or the gas particles flow out, we add in an additional step. Remember, I told you about charging up the watermelon and pushing it out at extremely high speeds. Now in Hall thrusters or ion thrusters, this is exactly what we do. We take the gas that's about to come out, we ionize it. We generate a plasma, right, by ionizing it. And remember, a plasma is essentially a collection of charged particles that are affected by electric and magnetic fields. What do I do next? I put electric potential between two plates, and the electric potential essentially accelerates my particles to extremely high velocities. And that is how I get the 50 kilometers per second exhaust velocities for my propulsion system. So this is a very elementary explanation of how my Hall thrusters work. The next slide gives you the physical representation of what's going on. I'd like to draw your attention to this phallic looking thing over here. This thing is called a cathode, and the cathode is the most useless component of a Hall thruster. Even though it's the most useless component of the thruster, without it, it cannot work. Okay, this forms the basis of my talk, the technical talk later on. Okay, the only thing that the cathode does over here, as you will see later on, is it will provide electrons to the entire system. That's all it does. Okay, just remember that's all it does. Okay, so this is what happens inside a Hall thruster. Okay, in 1 minute. Okay, these gray lines that you see over here, these are magnetic field lines. And magnetic field lines, right, essentially can control and confine the trajectories of the electrons. Now, what happens is you get these magnetic field lines by having either a magnetic coil over here, or you have permanent magnets from here to here. The cathode ejects this particle we call the electron, and the electron is confined within this magnetic field lines, and it gyrates about its orbit like that. What happens next is, this is one electron. The cathode it essentially fires out numerous electrons. You have a collection of electrons over here that are trapped, they are spiraling at extremely high velocities. What happens is behind, we inject propellant. These are neutral xenon gas, right? And upon interaction and collision with one of these electrons, which are moving at extremely high velocities, it ionizes, right? Generating a plasma. When you have a plasma, remember what I said earlier on, you're able to accelerate these charged particles at extremely high velocities, generating a significant amount of thrust with a very little amount of propellant. And this can therefore later be put on board a spacecraft for these kind of fanciful missions. Okay? So I've talked so much about it, but why haven't people really done it? What's the real challenges? You need to understand the challenges behind the propulsion systems in order for you to deploy. And this is not just talking about electric propulsion systems. We're talking about all systems that want to deploy propulsion up in space. The first thing we talk about is in the satellite bus itself. When we're talking about, when we are miniaturizing our platforms, smaller and smaller, the key problem really is in the power that you utilize, right? Because in small platforms like about 3U satellites, 6U satellites, you don't have the sheer power to deploy operations. Let's just say if your propulsion system takes out about 90% of the power budget on board your satellite, it doesn't make sense for me to deploy a whole platform just for me to run a thruster with no budget for me to deploy my application, right? So the power is very important because you don't have the space for the solar panels or the batteries. Second thing is in miniaturizing the systems, the architecture becomes a little bit more complex. For example, when I'm limited by the space that I have on board my platform, there's a limitation to how much I can pressurize my tank. Too much, it explodes. And that becomes even more challenging if I go smaller and smaller, where your walls need to be really, really thin for the mass of the entire system to be very low. The second important thing that we talk about in conventional systems or electric propulsion systems in satellites is ignition. Earlier on, I mentioned that the whole thruster requires a cathode, right? Now, the cathode has a long startup time in order for the electrons to come out to ignite the discharge. Okay? I'll talk about this later on, component failure together with the long startup time. This is really the cathode. The last thing that we really need to consider is in the lifetime of the system, and it's in two things. Number one is in the propellant. We don't want to make it a case where we deploy a cold gas system and maybe about 5-6 maneuvers, you run out of propellant, you cannot do anything already. We want to be able to continuously fire your systems. Second thing is in erosion. When we deploy our systems, we want to ensure that, we're talking about plasmas, right? Our systems will be able to extend the physical lifetime and in the process, do not damage the actual physical thruster itself due to erosion. So this is something that needs to be addressed, and we'll talk about it very soon. So indulge me in talking about cathodes. This cathode over here, this cathode over here, these are conventionally deployed on conventional Hall thrusters, commercial Hall thrusters. These are all commercial Hall thrusters. They are Chinese Hall thrusters. I did a lot of research on Chinese Hall thrusters. I'll give my opinions later when there's no video, right? But if you see, Chinese Hall thrusters, right? Majority of the Hall thrusters, commercial Hall thrusters being deployed on the market, all have two cathodes. And the reason why is because it's the first component to fail. I'll tell you why it's the first component to fail. Look at the first picture up there, the two pictures up there. Can you see that is glowing red hot? Now, if you have gone through an elementary course in physics, you understand that in order for a cathode to work, right, all it does, right, is this thing called thermionic emission. Thermionic emission essentially is the process, right, where you heat something to extremely high temperatures and you start emitting electrons. And that's how the cathode works. You heat something to extremely high temperatures like this, and you start to emit electrons. The real problem really is, like I mentioned before, because of the cathode going up to these kind of temperatures, right, you cannot fire your thrusters on demand. You cannot push button and say, I want my thrust. I have to wait for this entire cathode to warm up, and then my thruster can fire. Extremely bad, because let's just say you need to do a particular maneuver in orbit on demand. You can't do this. Okay? The second important thing is, if you keep heating, then removing the power, heating, then removing the power, heating, then removing the power, it causes a lot of thermal stress to the system itself, and this is the reason why the cathode fails. The final thing about the cathodes, right, is that it consumes a lot of power. about 80 to 90% of the power goes just into heating. It does not contribute to generation of the thrust at all. It just lights up and ignites the entire discharge. This is the reason why I feel that if I were to design, or if my team were to design something like a Hall effect thruster-based system, if we could just get rid of the cathode, and you don't see a cathode over here, wouldn't it be nice? Okay, we'll talk about my technology later on. Oh, is this slide already? That's that fast. Okay, so this is a slide. 3 things that we need to address, remember. Okay, so the first thing that we need to address is the power itself. Conventional Hall thrusters, due to the fact that it requires a cathode for it to be functional, they usually operate at hundreds to thousands of watts. This Hall effect thruster that you see over here, that I'm holding in my hand, is functional at just half a watt. I stress test this at NTU. Okay, there is no other Hall thruster in the market which is functional at just half a watt. And in fact, if to put things into perspective, if you talk about any other kind of propulsion system, let's just say a coal gas thruster, to just open the valve is more than half a watt already. This Hall thruster is operational at half a watt. So I like selling koyuk like that. Not intentional, but I'm just trying to say this. It does its job at half a watt. Second thing that it does, remember I talked about ignition. Right? A conventional Hall thruster requires a cathode for ignition, and the cathode really, my point, right, in developing these systems is I want it to be operational. From an operational standpoint, right, I'm not chasing after high thrust, I'm not chasing after high efficiency. I want to make sure, right, that when I press button, right, it can turn on demand. I need to say this is not sexual, because a lot of people always laugh when I say turn on demand, okay? Not intended. Anyway, this is turn on demand. You press button, you get it, okay? And the real reason is because there's no cathode as well. There is some technical innovations that goes on behind this that allows for this to be possible. And this is something that we'll IP with the university. Okay? The last thing that we have designed, and this is extremely novel, you'll see in the pictures later on, maybe you can edit the video later to not show that picture, okay? Is the fact that a conventional Hall thruster, if you see this ring over here, this circular ring, that's the plasma discharge inside a channel. And the plasma discharge inside the channel, right, really is the reason, key reason why a Hall effect thruster fails. Because you have a collection of very high energetic particles within a ceramic chamber, causing erosion to the channel. What you'll see later on in this system, this is an external discharge plasma thruster, where we confine the electrons outside the system. And for so long, right, that we had this idea, we have done numerous numerical simulations on this. There's actually quite deep physics in this kind of thrusters that we've just developed. No papers written about it yet. We are just starting to understand what goes on inside. Everybody that I've met from different entities, it could be funding agencies, it could be from VCs, it could be people who are technical and competent in the field. They always ask, is the physics sound or not? The physics to me is always sound. As a physicist, this is something that I always have to cross-check multiple times. The second important thing, right, is, so you say the physics is sound. Does it really work? Can you show that it works? I had no money. It was really, really difficult for me to demonstrate something like this. So there was a lot of sacrifice in order for us to demonstrate a system like this that you will see later on. Okay, so that's the set story aside. This is something that we will be developing very soon. So this will be something that we want to flight qualify. It's an integrated 1U system and comprises not only just a propulsion system like this, it will also comprise of a tank. We call this a fluidic regulation system, a power processing unit and controller. And essentially all this does, right, is it allows for rapid integration of our propulsion system on board any platforms that wants to go up to space. Now, this is extremely important now to show that we are able to compartmentalize everything into 1U. The real reason is because, let's just say I want to develop telecommunications payload, or rather an entire satellite doing telecommunications. If I want to put in a propulsion system, right, I don't want to re-engineer my entire satellite. All I want to do, right, is I just want to take one cube, like Lego like that, and then tap into my entire system and it can fly. This is what we're trying to do. Modularize everything such that when something is available for us to deploy, you can take out what is not necessary and we can put in accordingly. This is what we're talking about. This is NewX1. NewX1 essentially is a collaborative endeavor between New Space, a startup that we talked about based in NUS earlier on, and Aliena. So essentially, New Space has a goal to deploy a constellation of 35 satellites for IoT purposes. Of course, they have a huge experience in satellite engineering, and they're the perfect partners for us to do a technical demonstration. So a technical demonstration is slated to take place next year, at the end of next year. Now, what will it showcase? Three main things. Number one, it showcases that our propulsion systems work, okay? Very baseline lah, we can switch on. Second thing, it showcases that there are payloads that they deploy and their satellite engineering capabilities, right, they are really physically sound lah. The third important thing, which is important for both of us, is to show that we are able to integrate and we are modular, meaning to say they can work with another commercial entity and we can work with another commercial entity to quickly put together systems that can fly out into space. And this is important again because if you want to work with another commercial entity, they're going to question whether, hey, have you worked with other commercial entities before or not? We want to show that we can do this together, we can do this well. So these are the goals of the technical demonstration next year. Key things to note also will be that this platform will be the world's first 3U satellite to house a fully functional Hall effect thruster. It's never been done before. So we want to be able to show that even a small platform can house a Hall thruster. And a Hall thruster really is a system developed and deployed since the 70s when it was first commissioned by the Russians. And it's really still the propulsion system of choice. SpaceX, a constellation of 12,000. Every one of those satellites eventually will contain a Hall thruster. 60 satellites just went up, all of them had a Hall thruster. Amazon's Project Kuiper, they all will carry a Hall thruster. I know because their procurement officer is already looking out on the market for specific thrusters that can fit their applications. OneWeb, their entire constellation will also carry Hall thrusters. So Hall thrusters, we can do it, but our added merit, right, is that we are able to scale it into a platform that small, 3U, to actually house something that functional. Okay, these are our recent activities, but what we want to highlight over here. We have done prototyping is in my office. Satellite Research Center, we have fired our systems already, it's done. We're actually selling this module already. We're starting to sell, do pre-sales. In fact, if you are interested, you can talk to me after this, I can sell you. I'll give you a sort of idea of the scale of matters, why we decided to go into Hall effect thrusters. When we started developing propulsion systems, right, we never really started working on Hall effect thrusters. We wanted to work on some other systems. And knowing that Hall effect thrusters had a long legacy, being selected by NASA, JAXA, and ESA as the propulsion system of choice on board governmental platforms, larger platforms, we realized that any propulsion system that we want to demonstrate has to be benchmarked with a Hall thruster. Now we went out to many companies, the big five, Ariane, Busek, CSC, Zhonghangtian, wanting to buy a Hall thruster. A Hall thruster that is commercial on the market costs anywhere from 1.5 million US dollars to 2.2 million US dollars. Now that is crazy because the amount of funding that we got for the project is less than 1.5. Okay, so just to buy something to benchmark the entire system that we're trying to develop, we waste everything. So it doesn't make sense. We decided, hey, if Hall thrusters are so expensive, right? We just do it. We do it better, and we make it accessible and available to anybody who wants to procure a system like this. And indeed, we did. And indeed, this is something that we want to make available to commercial entities at this moment. And this is why we are trying to sell this at the moment. Okay, so we're glad to say that patent provisional filing has been approved. Presentation, right? I just want to show that commercialization of products in space, some of you all might not be clearly aware at this moment. It really depends on viable applications and service. So for example, if there's no demand for me to put up a satellite in space, right, there's no point for me to develop something like this. Yet, at the same point of time, okay, applications, okay, the people who want to deploy it, whether they want to deploy it, right, really hinges, the determining factor really is on whether the technology is mature enough. And this really is a chicken and egg question. Because if there's nobody who wants to use it, why develop the tech? And if the tech developers don't see that there are no applications for you to service, why do you go into something like this? So it really is chicken and egg. What we want to show is we want to be able to catalyze growth and development for space in Singapore by lowering the barriers to entry, again, through being able to translate technologies from a low TRL level to something which is slightly higher. we also want to be the mouthpiece for the space community, space industry, to tell terrestrial-based operators that space is really an option, opportunity, huge opportunity for you to acquire high resolution and high quantity data. And there are truly numerous benefits to Singapore. This is something that we say a lot to government officials. Hundreds to thousands of jobs for the ecosystem itself. Talent development, huge important thing for us to partner with IHLs and faculty as well. Gives faculty a new area for them to work on challenge problems and topics. At the same point of time, these guys will come back into the pipeline for us to service the entire industry accordingly. Attracts a lot of foreign investment and talent. We build up together collectively a space ecosystem that is not really consolidated at this moment, but we're trying to drive this. Of course, it's also very good for our defense and homeland security applications. It enhances our diplomatic ties with our partners. For example, Northern Territory that I will not talk about, I don't have time. NASA, UNUSA, JAXA, and so forth. Also, it allows for Singapore to establish dominance as a leader in space tech. Promotes STEM in education. This is very important. Something that's extremely close to my heart as well. Because you're in engineering schools, and engineering, right, is a course that only people who are passionate in engineering will go into at this moment. We need high quality engineers to service the public service, to service the private industries as well. Okay, we need a lot of high quality engineers. We see this a lot in the States as well. When the Apollo missions were cancelled, right? You realize that the number of people going into engineering fields, they actually declined. If you see, another case is in Israel, where they had that attempt to land Bereshit on the moon. Suddenly there was so much interest in engineering down there. And we believe that, going up to space, right, or rather having a very bustling space community in Singapore will actually encourage more students to really consider STEM. Not everybody will go into space, but as long as you have that interest in developing commercially viable products that can benefit society, engineers, we need a lot of engineers, that's good enough for me. That's good enough for me. Okay, yeah, and economic growth and showcase of translation efforts. This is very good for the universities. Okay, so I think, how many slides do I have? 2, 3, 3 slides. Okay, internships and opportunities available. At this moment, right, I'm looking for interns. From the NTU ecosystem, I'm very familiar. I do a lot of short haul projects or FYPs even. FYPs can be in the form of a 1-year attachment together with a company. It could be attached with one of the faculty. I can stand in place, come up with a challenge topic. It might not necessarily have to do in the commercial engineering aspect of a propulsion system like this. It could be in the form of just investigating the physics behind something like this, or maybe a different product. We are looking for short-term research interns. We call them space engineering interns to make it sound a little bit more sexy, huh? Give a nice title, then people might consider, right? Okay, what kind of people that I'm looking out for? I'll go through this later, but the most important thing is for me to emphasize, right? I don't need someone with a perfect GPA. I don't need someone with high GPA. I don't need someone who has many years of experience in propulsion. I mean, that would be good, but we don't have that in Singapore. What a lot of people in Singapore are looking out for, right, are people who are independent researchers. Meaning to say, we throw a challenge statement to our interns, and there are good cases and examples of these people who function very well. These guys over here that you see, they're all poly graduates, right? Fresh out of poly, waiting to go into university. All of them got scholarships with the universities after that. But while waiting to go into university, right, into army, they work under me to commission the flagship space environment simulator in NTU. All I did to them, right, was to give them challenge statements. For example, I'll tell them that, I got a hall thruster down there. I need to measure the beam current at every point of time, or at every point in space at particular given point of time. A challenge statement is given to them. Whatever resources they need, I make it available. They'll go up and find their way in order for them to do something like that. Occasionally, they'll come up to me for certain technical help in understanding physical systems. Like, how do I measure current? Or how do I remove noise from a measurement? You can tell them. And this is the best way to learn. By throwing someone into the deep end of the pool, they engineer their way out. And this is how I learn as well. because again, I was never a space engineer. I was thrown in a deep end of the pool. I had to develop something like this, and I learned through doing. Okay, you see this in Singapore as well. In the 60s, in the 70s, right? We didn't always have engineers who could develop entire infrastructure for housing, for rails. But again, these tasks were thrown to very young engineers at the start, and they built an entire ecosystem out of learning from scratch. So who am I looking out for? And it really is dependent on your interests. I'm looking out for people who are interested in plasma physics and diagnostics to measure and understand the beam and the plasma itself. So if you are a physicist or budding physicist, want to know a little bit more about plasma physics, this is something that's in the pipeline. Space environment simulation. Again, we are going to build up a space environment chamber at Changi Business Park. If you're interested in understanding what goes on into simulating a space environment, want to build up vacuum systems from scratch, you can come in over here. Emerging propulsion systems. So again, I'm propulsion agnostic. Some people who are in the industry, right, they always believe if they work on propulsion, electric propulsion is this is the way to go. But I'm agnostic. If there are any other propulsion systems which you feel are highly disruptive, and you want to incubate somewhere and develop at a low TRL level, I'm happy to take you in to see how we can develop a system and co-develop something like that together. Software development and electrical engineers are very important for me because at this moment we can trigger our thrusters on and off. But more importantly, we need to be able to regulate our propellant to the system when we want it on demand and to trigger electronic systems to switch on and off. More importantly, we want this system to be able to speak with reaction wheels as well, to have full control over flight avionics in a satellite up there. Mechanical engineers, extremely important. We need people to design mechanical structures, run thermofluidic simulations for all of us. And fluidic regulation engineers are very, very important. Of course, if you're not an engineer and you also want to be a part of this entire endeavor, of course, we're looking for people who do BD, policy and public engagement. Okay, so there's always something for everybody. Now, what can you expect out of this entire internship and attachment? I can say that I am not KPMG, I am not a big four that can pay you a lot of money as an intern. Being realistic as a startup, we can pay fairly, okay? We can remunerate fairly, but not more, okay? What we feel, right, that we really could give a lot is in intangible benefits. I'm not trying to sell COVID over here, okay? You really learn to build infrastructure and capability for yourself, and this is extremely important. Let's just say you're not interested to do propulsion, you have some interest to do something else, but you want to understand how systems are being tested, what the entire developmental cycle is like for space. This is a perfect opportunity. Most importantly, if you are a budding academic, you want to write papers with me. I love writing scientific papers, but I don't have the time to physically sit down and crunch. So I need people to carry out the experiments with me, analyze the data, and we write some very solid papers, man. This is something that's still at my heart. I really, really want to do this. And I need people who can write papers with me, okay? Okay, so this is for internships. The second thing that we are trying to conduct, and this will be facilitated by Jun Kai, SETS, is we're organizing this outreach activity to very young students at SSTA. So essentially, right, we are doing this, long story short, we're doing a bottle rocket challenge, okay? I need you all to come in. It's just a 3.5-hour thing. You all will operate together with NUS. The NTU team also has their side also. So I understand that there will be 40 students. So the NUS team will take 20. The NTU team will take 20. Teach students on the fundamentals of rocketry. Develop the material with me because our call for meeting will all go through pedagogy, how to develop lesson materials and so forth, and execute the activity within that 3.5 hours with the students. Okay? So this is quite good because it gives a lot of publicity for SETS, show that you are engaged with the community, give you VIA hours. But most importantly, something that's also, again, very dear to my heart. At the end of the entire competition, of course, the outcomes is right. The kids get to hands-on, get to fire their rockets. Wow, it works. The most important thing, right, is we want to do a showcase of our local IHL system. After all the concepts that you have taught to the students, right, have been conveyed, they fire already, there will be a NUS/NTU SETS Challenge Trophy, where we want to show the kids, right, that this is how Koko and Tete do it, Okay, so this is how the big boys do it. And essentially, NUS and NTU, right? We just want to show that harnessing the expertise that you all have, physical concepts being taught within the local IHL system, you're able to come up with a very functional product, demonstrate that you can do something as well. This is very important for young kids because a lot of us, when we grow up in the local academic ecosystem, we always berate ourselves a lot. And something that I get a lot as well. I spent 10 years in NTU, and I always think that I'm not good enough as compared to someone who has had an overseas scholarship education. We want to go up to schools and tell schools and even young kids, students, that we in NUS and NTU, we can do something and we can do things extremely well as well. We want to show that our universities, we are truly world-class, and these students can really consider coming into the local university ecosystem when they are done with their studies in the mainstream education system. It is still a very viable opportunity, and it presents a lot of potential for them to further. Okay, so tomorrow something very important is going to happen. I'm not going to spend so much time on this, but watch out. We're doing something very big with the Australian Northern Territory. I'll be signing something with the Chief Minister tomorrow. Last slide. This really is my last slide before I end. I know it's been an extremely long lecture. But I think this is also extremely important to talk about. A lot of people have the misconception, right, that doing a startup is all about glamour. It's all about, traveling to fancy places, flying business class, wining and dining with nice people. But really, the story is far from that. It's more than, it's tougher than, there's no glamour at all. And there's so much sacrifice involved that a lot of people really don't see. Behind what you see on social media, right, what you don't hear about, okay, this is social media, by the way. This is when we signed our term sheet with Capvista. Happy day for us, right? Wow, fancy. This was at the exhibition at the Art Science Museum. Wow, big day for us, public showcase. Oh, people are really interested in our systems. This is me speaking at CNES, French Space Agency, together invited with EDB. The guys from ST were there as well. I was a small startup speaking at this platform, showcasing to the French ecosystem that we in Singapore also have products that may be of interest to them. So these are things which are glamorous, but what people don't see is the things below. Okay, this is the sacrifice that we have. What's this? This is an entire office that I rented for 7 days when I was up in France. Okay, so this is where I stayed. You see this chair over here? I slept on this chair. I had no money to buy a bed, or rather to rent a hotel. I slept on this chair, and all there was a table, and there was a window. There wasn't even a toilet. I had to exit this office and use a common toilet. So this was where I stayed. My back hurt for 7 days. This convention lasted 1 day only. I stayed for 7 days. Not because I want to go see Eiffel Tower. I had no interest in doing that. I just wanted to get home and do my work. Why I stayed there for 7 days is because the flights were cheap. I flew budget, extreme budget. And my transit time was, I transit many times. I mean, when you're young, right, you think you can do this. But when you're my age, I very mortal. I cannot do this anymore. This is Simon. I caught a picture of Simon outside Art Science Museum. He was sitting out there in his natural element, eating free food. Okay? You know what? I took this photo, right, not to laugh at him, because I was doing the exact same thing. And a lot of times, right, we as entrepreneurs, right, we take care a lot of our stuff, but we neglect ourselves. Because when you run a startup, right, it's not so much about making money for your own, but you understand that the people under you, they have their own livelihoods, they have children to take care of, they have mouths to feed, they have college loans to pay off, and these are the people that we really need to take care of before we even think about ourselves. Simon does this a lot. I do this a lot also. So yesterday when I talked, right, at NUS, there was refreshment after that, right, I tapao. Later I can tapao also. Okay? I very gain free food. Okay? This is me. Okay? Why did I take a picture like this? Okay, I was stranded in the airport for 25 hours because I missed my flight. Okay, I missed my flight because I flew budget. And of course, I had to transit many times, and because one flight was delayed by half an hour, another one was delayed by a little bit, I was trapped 25 hours. And then I had to spend extra money to buy new tickets. Wow, very sad. Why did I take a picture of this street? Because when I was stranded, right, I thought, happy, gay-kiang, right? Go outside, explore the city. Where was I? This is Warsaw. Warsaw, I don't it's in Poland. I wasn't even supposed to be in Poland, I was supposed to be in France, right? I transited down there. I thought, okay, since I'm stranded, right, I go and take a look at the city. I walk out over here, right? Within, I think, about a few minutes, I got robbed over here. I got robbed at knife point. They took my wallet. I don't know why they want to take my wallet. I got no money. But okay, whatever. You take my money, take my camera. I still stupid, ask them, hey, can you give me back my SD card or not? Wow, don't do that. Okay, don't ask for your SD card back. Because at that moment, right, he really wants to stab me already. I think he cannot deal with Asians. Okay, so this was me down there. This is a police report. And this really is a story. I mean, there's more to it than just the glamorous stories on that. Again, last few things. No shortcuts to success. There's no Dominics and Imrans, you know. Hi, my name's Dominic. Hi, my name's Imran. You want to be a millionaire like me? No such thing. Okay? No shortcut. You really sacrifice, give up a lot. Okay? Lessons in failure. I love people who fail a lot. I'd rather take someone, right, who has failed many times in life, done a lot of projects that never succeeded, because every time that they fail, right, they always dig themselves out. These are the kind of profile of people that we are looking out for. Again, different label or different odds. I don't need to talk about this for primary school kids. Sacrifice. You really have to learn how to sacrifice. As an entrepreneur, I learned that a lot. I'm still learning to give up a lot. And most importantly, you have to give back. You must dare to dream and dare to do. When you are able to come back to establish something good within the ecosystem, you always need to remember, right, that this ecosystem, right, can only grow if there are people coming into the pipeline to service the community, if there are applications to grow out of this entire thing. And these really are lessons in life taught to me by my mentor, Professor Lim Jian Wei. One of the things that he always tells me to do, right, is you don't just need to dare to dream. You need to dare to do, and you need to dare to sacrifice. If you can do all of this, right, then even if your startup or whatever you're pursuing is not successful, right, at least you know you learned something out of it and you did your best, and of course that teaches you more lessons than just succeeding your entire life and just going through textbooks and learning systems. Okay, so yeah, that's all I have for my talk today. Yeah. I can take some questions.
Yeah, Q&A. You got a question? I got a question, but
Yes.
No, it's not it might be proprietary.
Oh, proprietary. If it's technical, right? Not surrounding the physics of my Hall trusses. We can talk about it later.
Oh, okay, then I'll hold it.
Even so, I don't know whether I can tell you or not.
Okay.
Because you work very closely with George.
Yeah.
George will kill me. If you notice, right, the thruster is called Geo1.
Yeah.
Right, it's named after him.
Really?
It's named after him. I was a principal investigator, but I named it after him. Again, because I value his input. You have to be fair. I'm extremely fair person to work with. If you work with me, right, you notice that I don't want a lot out of these kind of endeavors. I just want to ensure that if I want to mentor students, right, they get to take away a lot out of this, more than I can give them. And that's really from the learning itself. That's extremely important. That's also the reason why I say I'm extremely selective when it comes to internship, because when I come to a point, right, where I realize that I'm not in a good capacity to physically mentor and sit down and go through problem statements with students, right, I will not take students really, because I don't want to shortchange my students. I never want to shortchange my students. Yeah.
You're sharing the longer term vision of like after what other launches are scheduled.
Oh yes. Do I have the slide over here? No, I don't have the slide over here. Okay. Can turn off the recording? So